All right, so a couple things off the top was already brought up. So I put up this practice problem this morning. It's just confidence, so I call it CI and HT. So confidence intervals and hypothesis testing. So we did confidence intervals last week. We do hypothesis testing this week. There's just some additional problems that you can kind of work to get a better idea of how you work through those problems or on those concepts. I've got the practice exams up there that have questions on there. Everybody did those as well. I just, I have one sitting around that sometimes if we have enough time, I might use it as an assignment. Sometimes I end up using it just as kind of an additional practice thing because I don't want you to have to do a whole other homework this week or this week. I want you to start to kind of study for the exam, but here's a tool that you can kind of help use, or you can use to help you study. So we've got, and I'll move that connected assignment down to the grade category. Once I go back in, I have to make sure I give everybody credit for 16. I forget it what I said in the announcement, but there's one of them that had a kind of a weird glitch in the algorithm, some of the random numbers it was generating. And then obviously Excel assignment, which is kind of over confidence intervals. And it has the end of it is kind of over hypothesis testing, although we have all the tools that we need. So once we understand hypothesis testing today, you probably could even start to get kind of work on that, and you might be able to kind of figure it out on your own. But I'll show you examples of that on Wednesday so that you can kind of final or finish that. What else do I want to say here? Any questions for me before we kind of jump into material here? I think that's actually for kind of housekeeping stuff. So we will have that in-class exam on Monday. The other thing I would strongly suggest is going through those practice exams, especially the early problems. You can even start working on those now. For the hypothesis testing problems, kind of more towards the end of the week. But I just think that going through those once, figuring out which ones you don't really know. You've got the formula sheet up there as well, so you can kind of have those formulas. Figure out the ones you don't know, then look at the answer. Well, look at the answer key to figure out the ones you don't know, and then once you see the correct answer, if you can't reproduce it, well, then those are the problems that you really should focus on, right? Because if you already see you can't get it the first attempt, you see the answer, you can't reproduce that answer, that tells you you're probably having kind of difficulty with those. Okay. All right, so jump in things here. I'll go through this first stuff kind of quick. It's really just conceptual and a little bit of terminology, and then we'll kind of break down more of the statistics side of it. So what we're going to be doing, so if we think about with confidence intervals, I was able to say, okay, I don't know where the population mean is, but based off what I saw from the sample, I can tell you with a certain level of confidence, it's somewhere in this range, right? And that was great if I could get a really narrow range of values. Right? So hypothesis testing is very similar. We're still interested in where that population parameter, whether it's the mean or the proportion is. It's just now we're going to rule out specific values, okay? So we're not going to give a range where we say we know it's within this range. We're saying, I can tell you with this level of certainty that that can't be the sample mean. And in fact, we're not just going to be able to say about one value. We can say that value or anything greater than it can't be the mean. Anything of that value or anything less than that can't be the true population mean. So it's still kind of trying to get an idea about where this population mean is. It's just now we're kind of ruling things out as opposed to like what we're ruling in. I guess if you want to think about that with confidence. So we're going to develop these things called null and alternative hypotheses. They're just complements of each other. So once you know the null, we'll automatically know the alternative. So this would be like if I said, so I guess I'll just start hold on that. So we have this null and alternative hypothesis. The null is going to be, well, this is what I'm going to assume is true. I'm going to assume that maybe the population mean income is, I don't know, 50,000, right? I'm then going to take a sample, right? And try to see if my sample mean goes against that. Like maybe I take a sample and I see it's only 45,000. Well, that goes against that assumption, that null hypothesis that it's equal to 50, right? 50,000. So my null hypothesis will be kind of what I'm assuming to be true. The alternative would be the opposite of that. So if I'm assuming that the average income is 50,000, the complement of that would be that it's any other value than 50,000. Right? Those are just kind of two complements, right? I assume it's one value. The complement of that is that it's any other value. Well, if I take a sample, right, and I see that the sample mean is 45,000, Well, that's evidence that goes against what I assume to be true, that null hypothesis. It's not 50,000, right? So it goes against that. So if we can find sufficient enough evidence from our sample, right? If the sample mean doesn't line up with what we assume about the population mean, we're going to reject that null hypothesis, right? And basically be able to say, based off the sample I took, I'm telling you that I can reject that assumption. It can't be that the true population mean is equal to 50,000. We don't have sufficient enough evidence, then we won't reject it, right? So even in my example where I said I saw a sample mean of 45,000, well, if we just go back to what we know about sample means, we know that they're normally distributed as long as we get a sample size over 30, and they're going to be normally distributed around what value? The mean of our sample mean should always be just that population mean, right? Whatever the data we were sampling from, our sample means are always centered around whatever that true population mean was. That's how we started to build confidence, that led into the discussion of confidence intervals. But we know that's going to be true about the distribution of our sample means. The problem is, it also has a variance, right? So if the variance is pretty high, like, I don't know, let's say the variance is 15,000, right? Well, actually, not even the variance. Let me do the standard deviation. All right, so let's say the standard deviation of my sample means is 15,000. Well, then, if I assume that that true population mean is 50,000, so if I'm assuming that to be true, then the sample means, if that is in fact true, should be centered around that value, right? But I saw a sample mean of what? 45,000? Well, that went against what I assumed, but I mean, with a standard deviation as large as 15,000, it's not that unlikely that even if that was the true population mean, that from just one sample, I might see 45,000, right? In fact, I might see 52,000 as my sample mean. That'd be pretty likely given how large that standard deviation is, right? Now, what probably would be likely, right? Let's say I saw a sample mean of 100,000, right? Well, that seems like if the true population mean was 50,000, this is what, like 5 or 6 standard deviations away? It's pretty unlikely I would see this from my sample mean if this was in fact the true value. So if I see something this far away from what I assume to be true, the probability is that that's not true, right? Because the probability of seeing this value would be so small that there's no way this could actually be the true population mean. It's probably more likely that the true population mean is somewhere a lot closer to that sample mean value I saw. Okay? So when we see things that are inconsistent with what we assume to be true, we can reject the null. But sometimes, right, for the values that, here aren't very far away from that assumption, well, maybe I don't have enough evidence to be able to reject it. Yes, it's inconsistent with what I assume to be true, but based off what we know about the sample mean distribution, it's inconsistent, but any one sample is going to be a little inconsistent with what that true population mean is, right? It's, what would let's say the actual population mean was 50,000. What's the probability I see exactly 50,000 from my sample mean? This is a normal distribution, truly continuous. The probability of seeing one specific value should be 0, right? So we're almost guaranteed to see a sample mean that's going to vary from that true population mean, right? It's just, does it vary enough from what we assume to be true that we can reject it, okay? So that's kind of the idea of what we're doing. I've got an example that we'll end up kind of working through with some actual numbers later on, but this might be something like, you want to know whether or not the average mass market beer has ABV different than, I chose one specific beer, but basically the value of 7%, right? So I take a sample of 36 and I see this sample mean of 4.5. Well, that's very inconsistent with what this value is, right? If I want to know, does the average mass market beer have a lower no, it's not, because I didn't say I assume it's equal to it. I said, I want to know whether or not it has an ABV lower than that, right? Well, it is lower than that, right? But is it inconsistent enough with that it's far enough away from that 7% value that I can reject that, right? So that's the example we'll kind of end up working through with some actual numbers. We got to go through a little more terminology first, okay? So this null alternative hypothesis, I kind of already explained the idea, is basically the null is just what we're assuming to be true. And the alternative is the exact opposite, the complement, or I think I said here, the contradiction of that, okay? So once I know the null, I automatically will know the alternative, right? Because it's just the complement of the null. Okay. So I'll write the null hypothesis H subscript 0, and then I'll always kind of write the alternative hypothesis H subscript A. You might see in the connect practice problems, they'll use H subscript 1 occasionally. I think in some of the slides I may even use that just to kind of, so you get used to kind of seeing a little bit. But when I'm writing the exam and then kind of look at that, those practice exams, I always use H subscript A. To me, it just makes more sense, right? Alternative hypothesis, and then null, kind of meaning 0, H subscript 0. So we can kind of think about, we're going to have a couple different scenarios. One where we reject the null hypothesis because we found evidence that was very inconsistent with the null. I kind of already went over this, I jumped the gun a little bit. But then there's two other scenarios where we fail to reject the null, right? One would be we find evidence that's not inconsistent with the null, right? We find evidence that actually supports it. So I gave the example initially that we were assuming that the value is exactly equal to, say, 50,000. But what we'll sometimes do with the null hypothesis is look at a range. So I might assume that the true average income is $50,000 or less, right? Well, if I assume that the true population mean is $50,000 or something below that, well, then seeing a sample mean of 45,000 would have actually been evidence that was consistent with the null or not inconsistent with the null. So we're not going to reject it if we found something that supports it. Now, there are other situations where we do have evidence that would go against the null, but does it go against enough? No, so we'll fail to reject. Okay. So I'll kind of give the analogy of a court case because I think it kind of helps just think about conceptually what the null and alternative are. So if the null is the assumed true state of nature and the alternative hypothesis is the complement of that, what are we trying to test with a court case? We're trying to test for whether or not someone's guilty, right? That's what we want to test for. Okay. So we're going to say what we want to test for, if we get to write this down, is the alternative hypothesis. Just a good way to remember, I think it's not the most technical way, but what we're trying to test for, or what we're trying to find, that's our alternative hypothesis. So what we do is we stack the deck against ourselves and assume the opposite is true. Well, for assuming the opposite, the alternative and the null, those are opposites, right? Those are complements. So here, if I want to test for whether or not someone's guilty, that's my alternative hypothesis. So what should my null be? I'm trying to find that they're guilty. I'll assume that they're innocent, which is what our court system is supposed to do. I'm not sure it always does it, but right, you're supposed to assume, right, that you're innocent until proven guilty, right? But the whole reason you're there is not because they think you're innocent. The whole reason you're in that courtroom is because they think you are guilty, and they're trying to show that. But they stack the deck against themselves and assume you're innocent, right? So our alternative hypothesis, what we're trying to test for. Okay. And we can kind of think about, if I have enough evidence, right, to reject the null, right, you don't have an alibi, you were seen near the scene of the crime, I don't know, they find a murder weapon in your home, right, that's enough evidence that goes against the null that you're innocent, that, right, you reject, right, or we reject that null hypothesis. We can find enough evidence that goes against you being innocent, we reject that you're innocent. And then obviously, like, if we didn't have sufficient enough evidence, it doesn't necessarily mean that you're innocent. It just means we don't have enough evidence to say that you're not. Just like I might find some evidence that goes against the null, but it just might not be enough evidence, right? So I'm not necessarily saying what I assume to be true is in fact true, right? Everyone that's found innocent isn't necessarily innocent. We just don't have enough evidence to say that they're not. Yeah.
How do we know when enough evidence?
Yeah, so that's going to be that I think I had some on, right? But so that's going to be the real question. That's the statistic side of this, right? Which is how far away from that assumed true value is too far, right? How far away from that assumed true value can I start to reject it, right? So we'll use a little bit of what we know in order to determine. I think it's the next slide, but we got one more terminology thing to get through, and then we'll start addressing it. So we've got this null and alternative. The three different types of tests we are going to have are the following. Right? And this is kind of how we'll write this out. Right? So don't, it's a lot of math. Don't get too, it's not that bad, right? So we've got, here's our null hypothesis. Here's all our alternative hypothesis. All we're going to do is assume. So if I'm just going to write out the null for you, and I'll put some numbers to it because mu subscript 0 here, that's just the value we're assuming. So maybe we assume that it's equal to 50,000. All right. So mu subscript 0, that's just going to be the value that you're testing against, right? Or you're testing for. We could also do that it's greater than or equal to a specific value. And then you could also do that the true mean is less than or equal to some value. Okay. So you'll notice the equality is always in my null hypothesis here, right? I think if not before this exam, at some point, we'll kind of keep doing some hypothesis tests and stuff after the exam. So I might kind of show you why it doesn't matter, but I don't want to waste time with that right now. But we just conventionally, right, well, we kind of have to keep the equality here if we're assuming it's exactly equal in value. But on the other two types of tests, we'll keep the equality in the null hypothesis. Now notice, if I'm assuming that the true population mean is less than or equal to 50,000 or some value here, well, the alternative of that would be that it's less, sorry, I had less than or equal to. The alternative would be that it's greater than 50,000, right? Or the complement of that. So we'll call these tests, these first two, one-sided tests. You can kind of think about why. Well, I'm saying assume that it's 50,000 or anything below it. Or assume that it's 50,000 or anything above it. Okay. So those are our one-sided tests, greater than or less than test. Greater than, less than, and notice those are lining up. The way that we reference these tests, it lines up with the alternative hypothesis. So to tell what type of test you have, whether or not it's a greater than, less than, or this final one we have talked about, not equal to test, all you're doing is looking at that alternative hypothesis. Notice not equal to test, we got not equal to sign an alternative hypothesis. Less than test, less than sign an alternative hypothesis. Greater than test, greater than sign. Okay? Now, as we start working through these problems, I might kind of refer to these as right and left tail, right? Well, think about why. If I'm assuming that it's a value or anything to the left, I'm looking at the left tail. If I assume that it's greater than a value, I'm looking at the right tail of the distribution. So greater than, less than, we can kind of also call those right and left tail tests. And then this not equal to test, sometimes we'll refer to that as a two-sided test. So the reason why, before we get to the statistics side of it, it'll make a little more sense why it's called two-tailed or two-sided. But you can kind of imagine, if I'm assuming that it's equal to 50,000, evidence on either side could go against that null, right? With the one-sided test, let's say I assume that it's less than or equal to 50,000 and I saw 45, well, that supports the null, right? So there is a range where you can kind of see the null supported. With a two-sided test or a not equal to test, it's guaranteed you're going to see something on either side of that value, right? So you've got both sides could be inconsistent with the null. Okay. Is that kind of making sense? Any questions just on the conceptual stuff so far? Yeah.
If it's like not in line with like what this says, is that when you reject it?
Yeah, it's possible we could reject it, right? So remember, if let's say I use this left tail test down here, where I'm assuming that the mean is less than or equal to 50,000. I then see 52,000 as my sample mean, right? Well, that is inconsistent with being less than or equal to 50,000, right? That number is actually greater than 50,000. In fact, if we see something inconsistent with the null, that actually means it's going to support the alternative. Because I'm kind of thinking about, there I saw, sorry, which value? Yeah, 52,000, right? I saw something that supported that alternative hypothesis. Okay. All right. So, any other questions on that before we keep? Does that kind of help a little bit? I get that the big reveal isn't there yet. It's probably frustrating, but right, we probably want to know, how do we know how far is too far, right? So we first need to be able to identify the null alternative because the way that we'll approach figuring out how far away is too far varies, okay? So the first thing we'll do is we'll figure out, are we talking about the population mean or the population proportion? That's a pretty easy step. I mean, that's kind of done for you in thinking about problems. we're then going to figure out, is it a one or a two-tailed test, or what type of tail test is it? Left, right, two-tailed, or greater than, less than, not equal to. We're then going to make sure we put that equality sign on our null hypothesis. This is always going to kind of be done for you. You really don't have to worry about this step too much. Excuse me. And then once we have that, we can kind of write out what our null alternative are. Okay. So we'll go through a couple examples. I think it'll kind of help to see how these steps would play out in an actual problem. So if we go back to that problem where I said we want to test for whether or not the average mass market beer has a lower ABV than 7%. So remember, the alternative hypothesis I said is what we want to test for, right? So what do I want to test for here? You kind of probably easier to always start out writing your alternative hypothesis. So my alternative hypothesis here is that true mean ABV for these mass market beers is less than 7%. That's what I'm trying to test for, right? Is it less than that? So the null, I'll stack the deck against myself and assume that the true mean is in fact greater than or equal to that 7% value. Okay. So when you read these problems, always kind of start out writing your alternative hypothesis. And then once you have the alternative, the null is just the complement of that. Okay. Any questions on why that is what it is? So I think the key to remember, the alternative hypothesis is what you're trying to test for. Here we're trying to find whether or not the average ABV is below 7%, or the true population mean of these mass market beers is below 7%. Okay. So, you know, I kind of wrote this out in English, but really how we're going to want to write this in terms of statistics is how I had it up here on the board, right? Kind of writing out that null alternative hypothesis. Now we know what type of tail test we have, right? So what type of tail test would I have here? Remember, the type of test we have is always based off of the alternative hypothesis. So here, I've got a less than or a left tail test, right? Looking at that left side. So here, I know I'll only reject the null hypothesis if I see a sample mean below what value? Well, if I'm assuming that it's 7% or higher, what are the only sample means that are inconsistent with that? I mean, I'm not looking for one value there, but like, if I'm telling you, I don't even know, actually, we could use this thing, sorry. If I'm assuming that it's somewhere in this range, 7% or higher, the only sample mean values inconsistent with that are ones that are less than 7%, right? Or sample means that would support the alternative hypothesis. Questions? Got another one. So let's think about a different example. I think these are a little bit easier, right? So when it comes to kind of identifying the alternative and null hypothesis, when you've got a left or right tail test, right? I said you always start out kind of what you're testing for is your alternative hypothesis, so I would write that out first. Right? So here, if I want to test for whether or not the mean retirement age is different than 67, what would my alternative hypothesis be? What am I trying to test for? If I want to test for whether or not it's different than 67, what I'm really saying is that true population mean different? Well, sorry, you can't really see that. Different than, not equal to 67, right? And I mean, that's what I'm trying to find. That's what I'm trying to test for, right? Is that mean retirement age different than or not equal to 67, right? The way we usually speak in English is we say it's different than a certain value, but we're really saying it's not equal to that, right? So anytime you see this word different than, think two-tail test, right? Because different than means you're always going to have this not equal to sign in the alternative hypothesis, which means the exact opposite of that. If the alternative hypothesis is not equal to 67, the null is, well, I'll assume it's equal to that value, right? I'm going to stack the deck against myself. I'm going to assume it's 67. And then if I see evidence that's different than that 67 value, maybe I can reject the null. Okay. So here we would have, oops, B would be the right answer. I guess I didn't have a red box around it like I thought I did. I So here we would have a two-tailed test, right? Not equal to sign will be a not equal to or a two-tailed test. I'm going to, well, I'll talk about type 1 errors. I'm going to skip the type 2 error discussion for now. It's not really overly important with how we're going to kind of start out. Maybe after the exam, we'll kind of revisit it. So you can imagine, let's say I had the mean retirement age example, where I'm assuming that that true population mean value is 67. Okay. And then maybe I see, I don't know, 82 from my sample, right? Well, that's pretty inconsistent with what I assume to be true, right? That's pretty far away, especially if, I don't know, let's say the standard deviation on these sample means was like, I don't know, 3. Well, that's like 5 standard deviations away or more. It's pretty far. It's pretty inconsistent with what I assume to be true. So I'm like, all right, pretty inconsistent with what I assume to be true. So I'm going to reject the null. It then comes out, somehow I get my hands on the population data and I figure out, actually the population mean was exactly 67. I just so happen to have one of these really, really, really low probability samples. The probability of seeing that sample was really low. I just got unlucky and I ended up having that one, right? So we would kind of call this a situation where we rejected the null, but we shouldn't have, right? So that is a type 1 error, right? So that's what we want to try to minimize, right? So we don't really want to make these errors, right? We want to be rejecting the null correctly, right? We don't want to be rejecting it when we shouldn't. Now, a type 2 error is the exact opposite of that. It's going to be something like, well, I'll try to give you some insight into it. Let's say I saw 68 as the sample mean. And I say, well, look, that's not even a standard deviation away with what I assume to be true. So that assumption very well could be true, right? Yeah, I found evidence it's inconsistent, but not very inconsistent. So I'm not going to, reject the null. Then it comes out later that the actual true population mean was 83. And I just so happen to get a really unlucky sample from that distribution, right? Which is kind of in the opposite direction. So here there was a situation where I didn't reject the null, but man, I really should have, right? Because the true population mean was way away from that. So that's a type 2 error, right? When we fail to reject the null, even though we should have. Now, we're talking about these errors as though like I can always go back and figure out if I made one. I mean, we usually aren't able to get hands on the population data. It's just that we know these situations can exist, right? It could be that I'm rejecting the null, even though I shouldn't be, type 1 error. And it could be that I'm failing to reject the null, even though I should be, or my type 2 error. So you can kind of think about this little grid, right? Like anytime I reject the null, and in fact it ends up being false, well, I made the right decision. If I failed to reject it and ends up being true, I made the correct decision. And then kind of when they're opposites, right? They don't line up. When I rejected it, even though I shouldn't have, type 1 error. When I failed to reject it, even though I should have, right? Because it ended up being false, my type 2 error. Okay. So look, type 1 error, we'll kind of use alpha to kind of represent how often we're going to be making these errors, right? So once we get through the process, we'll end up figuring out that just like confidence intervals, I can reject the null with different levels of confidence. And those confidence levels are going to correspond to alpha very similar like the confidence intervals did, okay? So if I want to say something with 95% confidence, we kind of use the same idea as confidence intervals, what would alpha be there? Well, alpha is still kind of representing what's outside of my confidence interval in decimal form. So 5% will be outside, 0.05. Same process as we're using for the confidence. So alpha is just kind of the decimal form of, whatever's outside of your level of confidence. Okay. So we're going to end up choosing alpha, right? We're going to basically choose the amount of type 1 errors that we want to make, right? So if we want to say something with 90% confidence, we're essentially saying that we're going to make errors 10% of the time, or the proportion of errors, alpha would be 0.1. We want to do the 99% confidence level. Well, then I'm going to be making errors 1% of the time, or my alpha, the proportion of errors I'm making, 0.01. Okay. And then I always like, is it kind of fun example. Just remember type 1, type 2 errors, right? you start out kind of assuming that the person is not pregnant. Well, here you rejected the null when very clearly you shouldn't have been, right? You made a type 1 error. Here, if you assume they're not pregnant and you fail to reject the null, well, you clearly should have been, right? So kind of type 1, type 2 errors, or when those two things don't line up. Another way to kind of relate this to some stuff we talked about before, type 1 error is like a false positive, right? I rejected the null, even though I shouldn't have been. Right? It was a false positive. I shouldn't have been rejecting it. All right, so type 1 error is when we're rejecting the null, even though it's true, right? We'll kind of use alpha to kind of signify the proportion of errors that we're making, right? 1 minus alpha would be probably not making a type 1 error. Right? This is not really that important. I kind of already went over this, right? Thinking about alpha just corresponding is the decimal form of whatever percent would be outside of your confidence level that you want to reject that null hypothesis with. Skip type 2 error for now. So what we're going to end up, how do we figure out how far away is too far? Okay. So I'll have this summary slide up here, but I'll walk through a couple of these on the board to kind of give you an idea what we're doing. So let's start out with a left-tailed one. And kind of think about it as I've got some assumed true value. In fact, I think I'll jump the gun a little bit so we can kind of get one of these examples in. So let's say I started out assuming that the average mass market beer has an ABV of 7% or greater, right? That was my, go back and add what? My, we assumed it was greater than or equal to 7% because what we were really trying to test for, or the alternative was that it was less than, right? So we have this left-tailed test. So I know that the only way I'm going to reject my null is if I see evidence inconsistent with that. Well, the only evidence inconsistent with being greater than or equal to 7 is being below 7, right? So how far away is too far? Well, we're going to use what we know about the normal distribution. So I know that I can turn a normal distribution into a standard normal distribution, right? Taking a certain value, subtracting the mean, dividing by the standard deviation, we plot that z value. There's going to be a z value that corresponds to the probability of seeing something that many standard deviations away or further is the probability that I want, or alpha, right? So let's say alpha is 0.05 just for the sake of this example. So I know that if I want to make errors 5% of the time, right? Even if, so let's assume this in fact was the true value. Well, even if this ends up being the true value, the value I assume ends up being true, there's going to be times when I see evidence that's really inconsistent. Yeah, the probability is small of seeing those sample means or that evidence that's really inconsistent, but there are still going to be times where I see those sample means. Well, I'm going to choose what percent of times I want to see, or I'm going to choose the cutoff for the probability. Like, think about it this way. As I move further away from that assumed mean, the probability of what I'm seeing is getting smaller and smaller, right? So, if I see something here, like 6.9, well, there's probably like pretty close to a 50% chance that I would see something below that, right? But if I get down to like 5.5, well, maybe it's only like a 20% chance, or probably 0.2 that I would see that. So what we're going to do is essentially set these cutoff values alpha, right? We're going to say, look, we're only going to want to reject the null if the probability of what we see falls below 0.05, this proportion of type 1 errors that we're okay making, right? So we're setting like a threshold probability. If when I see a sample mean value, so let's say I saw any sample mean out here, well, I know the probability of seeing that sample mean or anything below it would have to be less than 0.5. So I want to figure out kind of what that cutoff is, right? Well, I know the number of standard deviations away that cutoff would be, right? Because I know that there's going to be some z value that always corresponds from that standard normal distribution to 0.05. So I'll look up that area I want in the tail, that alpha value from my table. And just like we were for confidence intervals, kind of using that inverse process where I know the area in the tail I want. So I go to the middle of the table, find 0.05. Once I find that value, sorry. I started explaining confidence intervals. They're related. So let me try this again. So I kind of told you I'm setting this cutoff probability, right? If I see a sample mean value here, I know that when I turn this into a z-value, it's going to have an area that's less than 0.05, right? So essentially what I want to do is turn whatever my sample mean is into a z-value. Look that value up in the table, find the area to the left of it, right? So let's say I see a sample mean way out here, and I find that the area to the left of it is like 0.03. We're going to call that our p-value. Okay? So once I turn my sample mean into a z-value, I can find the area to the left of it. Okay? The probability of seeing that sample mean that I saw or anything further away from what I assume to be true, that's going to be my p-value. So kind of to reiterate, another kind of way to think about this p-value, the definition would be, it's the probability of seeing the sample mean that I did or anything further from what I assume to be true. Okay? So once I find that p-value, I'm basically going to compare it to that cutoff proportion that I set, or alpha, right? If the probability of seeing the sample mean that I did, or anything further from what I assume to be true, the p-value, falls below the kind of proportion of type 1 errors I want to make, then I'm okay rejecting that null hypothesis. Because essentially that probability has become so small that it's very unlikely that this is in fact the true mean. Yeah.
If you do the opposite, would it be if it's greater than?
Yeah, so let's think about, so this is actually probably really draw more board since they're here. But think about if I turn my sample mean into kind of a z-value here, well then for the right tail test, it would be the area to the right. But that definition of the p-value still applies because I didn't use directions, all right? I said it's the probability of seeing the sample mean that you saw or anything further from what you assume to be true. So for a right tail test, further away actually is going to the right. For a left tail test, it would be going to the left. Now the two-tail test gets a little bit tricky. So how are we going to find the p-value for a two-tail test? Very similar, but we have to think about now evidence on either side of what I assume to be true. All right, let's say I change this to a two-tail test where I'm just assuming the ABB was 7%. Well, then even if I still see that same sample mean, right, and I turn it into a standard normally distributed value or a z-value, I can find the probability of seeing something that was as inconsistent as what I saw from that assumed true value or anything further. The only problem is now something just as far away on the other side would have won against the null hypothesis as well. So the probability that I see any of these values, it was just as likely. I only get to see one sample. But if I'm looking at a two-tail test where I know I could see evidence on either side that was inconsistent, it was just as likely, and this will be negative since it's on the left-hand side. It was just as likely I saw sample means that were as inconsistent with what I assumed to be true, but on the other side. Right? That didn't exist for a one-tailed test because for a one-tailed test, if I saw evidence on the other side, well, that actually supported the null, right? It's just that now when I have a two-tailed test, evidence on either side is inconsistent with that null. Yeah.
So you only have to have one.
I'm doing this all based off one sample mean.
Okay, so
Yep.
you can't ever have, never mind.
No, you're right. I can never, well, I could like do multiple hypothesis tests, like keep taking more and more samples. But generally, you're going to have the sample data that you have. That is your sample, right? So you can calculate one sample mean. It's just that you know that if you could keep taking sample means, it was just as likely you would have seen values on the other side of the distribution that went against the null. Yep. So with a two-tailed test, once you find that area in the tail, right, because you're only going to have one sample mean, you just have to remember, oh yeah, there's an equally sized tail on the other side, or probability of seeing something inconsistent on the other side would be exactly the same. So you just multiply it by 2, right? Because, you know, I'm thinking about something just as far away, same number of standard deviations away, symmetric distribution. So I know that these two tails or these two probabilities would be exactly the same. So with the two-tailed test, we have an added step of once we find that area in the tail, that probability of seeing what we saw that was as inconsistent with the null or even more inconsistent, we have to multiply it by 2. Okay. All right. So, and then the rejection decision is the same for all of these. I kind of already had this up on the board, but if that probability falls below that threshold alpha you set, then you're okay rejecting the null. Because basically the probability of what you saw is so small, it's so unlikely that what you assume to be true is in fact true that you're okay saying it's not. Right? Now, if that p-value is relatively high, well, we're going to fail to reject the null, right? If the p-value is like, I don't know, 0.3, and I set alpha at 0.05, well, it's nowhere close to being less than that threshold I set. So we would fail to reject the null there. Okay? So this is our rejection rule. If your p-value or this probability of seeing the sample mean that you saw or anything more inconsistent with what you assume to be true, that falls below alpha, you're okay rejecting the null. Okay. So this is kind of, I guess, more of it, like how you would write out in math terms. I don't necessarily think it's going to help a lot, other than it kind of reminds you, whatever probability you find for a two-tailed test, you have to multiply it by 2. Okay. So let's work through an example. I want to put some actual numbers to this before we get out of here today. We can kind of review some of this next week. So here's just the steps written out. I'll walk through the steps at one time, or in the problem that we're doing, but it's always going to be figure out your null alternative. You're probably going to be told what alpha is, or you would choose the proportion of errors you want to make. Turn your sample mean into a z-value. So kind of what we'll start calling this is our z statistic, right? It represents the z-value of whatever sample mean we saw, or how many standard deviations away was the sample mean that we saw from that assumed true mean. Okay. So once we find that z-value, we can then find the probability of seeing that z-value or anything to the left of it if it's a left-tailed test, anything to the right of it for a right-tailed, and then compare that to alpha. Right, so these are kind of the steps. So how do I calculate that z-value? Well, we said if we have values for our sample mean, how do we turn that into a z-value? Well, we take whatever sample mean we see, we subtract the population mean, and then we divide it by, so remember this is the mean of my sample means is the population mean, and the standard deviations of my sample means was the original variance over my sample size. It's just, so the only thing different from what we were doing before, when we're looking at z statistics, which is why we don't call them just z values, but z statistics, is we can't see what that true population mean is. So what do? We're saying how far away is it from that assumed true population mean? So it's the number of, it's not the number of standard deviations away from the true population mean. Our z statistic will tell us the number of standard deviations, what we saw from our sample mean was, from the assumed true value. Right? So we could run hypothesis tests for multiple different values, right? So my z statistics will be the number of standard deviations away the sample mean I saw was from whatever I assumed to be true. Okay? So let's kind of work through this one. Okay. So I've got that same, we'll go back to, I think it was a left-tailed test. We said we wanted to know, was it less than 7%? So we assumed it was greater than or equal to. So we've got this left-tailed test. We took a sample of size 36, and we saw a sample mean of 4.5. And I gave an easy population variance here. Once again, it's going to be a little bit hokey. We're going to start out where how do I know the population variance but not the population mean? I described there are situations maybe, but we have to walk before we can run. We'll eventually, kind of like confidence intervals, show how we can do this with just the sample variance. Just like confidence intervals, it's going to be exactly the same. It's just we're going to have to use that student t distribution. Okay. So let's assume though in this one we've got the population variance. So I can think about, okay, I've got my sample mean distribution. I'm assuming, right, that's less than 7%. So we're going to use that cutoff value or that assumed true value of 7%. Now, why do I use 7 and not any other range there? I'll probably talk a little bit more about that on Wednesday, but if I can reject the highest value in this range, I for sure could reject any value below that, right? Because if I'm seeing evidence that's inconsistent enough with that null, right, that's, you know, greater than or equal to 7, well, it's going to be even further away from values that are less than 7, right? So, like I said, I'll kind of revisit that on Wednesday, but for now, just know that the cutoff value that you're using or the assumed true mean will just be whatever values in that null alternative hypothesis. So I see this sample mean of 4.5. What type of tailed test do I have? I'm looking for is it less than 7%, my alternative hypothesis. So we got a left tailed test. So I always just draw it out like straight in the air to the left, right? I then need to turn this sample mean value. Okay, well, what is the probability that I saw the sample mean I did or anything further from it? Well, if I can turn it into a z value or a z statistic, I can look that up in the table, right? So at this point, calculating a z statistic, it's just a matter of you've got the formula in front of you, you plug the values in, right? Now you could do the intermediate calculation here if you wanted, once again, just like confidence intervals, so I only have one value to plug in here, or I could just write it all out. Okay, so we had 1% was that population variance. Nice, so that made that a little bit easier. So I go ahead, I turn this into a z value, and I want to know, can I reject it? And here my rejection decision will be when the p-value is less than alpha, but my alpha here I'm told is 0.05. Okay, so I turn this into a z statistic. So let me go here. I'm going to cheat, right? If I turn this into a z statistic, I get negative 15. I'm using the extreme case in this first one to point something out. Obviously, there'll be more interesting values as we work through some more problems. But if what I saw from my sample, that sample mean, was 15 standard deviations away from what I assume to be true, what's probably true is that that assumption is wrong, right? Yeah, it'd be, I mean, I don't even have to go to the table to look this up, right? What's the probability of seeing something 15 standard deviations or anything below that? Basically 0, right? So if I've got a p-value that's basically 0, well, that's definitely going to be less than alpha of 0.5. So there, go all the way down, right? I basically can say at the 5% significance level, or with 95% confidence, I can reject that null hypothesis. Based off what I saw from the sample, the true population mean can't be greater than or equal to 7%, right? In fact, I could say it at really like any level of confidence. The p-value is so small, right? Even if alpha was like 0.001, right? 99.9% confidence, I could reject the hypothesis test here. Okay. So it's kind of using what we did before. All we're going to do is turn our sample statistic into the number of standard deviations away it is from the assumed true value. And if the probability of seeing something that far away from the assumed true value gets, you know, small enough below these threshold levels we're setting up for our type 1 errors, then we're okay rejecting, right? If it's not, then we would say we fail to reject, okay? And I thought this meme was funny at one time. I guess I've known people like this. So, so I think that gives us a good conceptual, hopefully kind of introduction to hypothesis testing. We can do this for sample mean. So just kind of I don't think we probably have enough time to kind of go through another example. I'll also kind of start off with that on Monday. But I want to kind of just give an idea of where we're going so you can kind of envision what we're going to be doing before the exam. So with confidence intervals, we built confidence intervals for sample means when we knew the population variance. We also did confidence intervals for proportions. So we're going to do hypothesis testing for examples where we turn a proportion into a test statistic, find the probability to sell that proportion. And the third and final one is the more realistic. We've got a sample mean, but we only have a sample variance. And the process for all three of these to find the p-value is exactly the same. The only difference is we're going to calculate the test statistics a little bit different, just like with the confidence intervals, they were a little bit different because the standard deviation of those statistics are going to be calculated a little bit different if you're talking about a sample mean versus a sample proportion. And then we'll have to use that student t-distribution if we only have the sample variance instead of the population variance. So on Tuesday, I'll introduce the last thing of hypothesis testing, which is not p-values, but critical values. They basically go hand in hand. It's just another way of thinking about hypothesis testing. So we'll finish up hypothesis testing, adding in this critical value aspect, and then we'll work through examples where we're dealing with sample proportions, sample means with known population variances, and sample means with unknown population variances. Okay. So we should be able to get through a good amount of examples on Wednesday. Friday, I said we'll kind of try to do some exam review. I'm probably going to plan on heavy focus on hypothesis testing. If you have other questions over confidence intervals or older stuff that we talked about from those practice exams, feel free to bring those questions on Friday. But I'll probably bring a set of questions that are really focusing on hypothesis testing, because I know it's difficult. It's the last thing that we covered. So I want to make sure we have as many examples as possible. Okay. All right. I'll see you guys on Wednesday.